Hadoop overview. In this section, I'm going to give you a high-level overview of Hadoop. Hadoop is a pretty big piece of technology. There's a lot of projects and sub-projects that come as part of Hadoop. There is no way we can do justice to Hadoop in one section. I have an entire course devoted to Hadoop called 605-788, which is Big Data Processing using Hadoop. In this section, I want to give you enough information so you understand what Hadoop is, so that you can understand what AWS EMR is, which is Managed Hadoop Service. So what are the objectives in this section? I'm going to talk about the Hadoop history, where Hadoop is coming from, the Hadoop versions, and then primarily we're going to talk about the Hadoop 2 technology stack, which is also called Yarn. Then we'll look at the Hadoop sub-projects that are there in the marketplace, and then we'll look at the Hadoop programming model, and then we'll look at the Hadoop distributions that's out there. Around 2002, a couple of engineers, Doug Cutting and Mike Caffarella, and by the way, Doug Cutting is the same guy who created Lucene, the Java search engine technology. They started working on a project called Nutch. Nutch was a distributed crawler and search engine technology. They realized that it worked fine for a few machines, maybe 10, 15 machines, but when it came to hundreds of machines, their system did not really scale. So they were kind of struggling as to what to do. In the meantime, around 2003, 2004, Google publishes a paper called GFS and MapReduce. Doug Cutting takes the GFS paper, which is the Google file system, and implements something called DFS, which is the distributed file system. He uses the GFS paper as the blueprint for that. And then he also implements the MapReduce technology. Google only publishes the paper, they don't give you the source code. So he uses that blueprint to create MapReduce, and he adds this support into Nutch. And the years go on. Suddenly, Yahoo hires Cutting and launches the project called Hadoop, which is an open source project, and they launch it off as a spin-off from Nutch. This is going to become the future of big data processing using Hadoop. So the project gets launched. Around 2007, an engineer at New York Times uses the Hadoop technology by launching about 100 EC2 machines in the Amazon cloud, loading image archives and converting the image archives from one format to another format. So that's actually the first example of Hadoop in the cloud that was talked about and written about in many magazines. Around 2008, Facebook launches Hive as part of the Hadoop ecosystem, a project that's built on top of Hadoop MapReduce that translates SQL-like queries into Hadoop MapReduce. In 2008, Yahoo, which actually started the Hadoop project under the leadership of Doug Cutting in 2006, break the record for a terabyte sort in 3.5 minutes by using 910 nodes. If you're going to be doing distributed computing, if you can break the terabyte sort record, that's an amazing feat. And that's what they did. In 2008, a company called Cloudera was founded, which started supporting Hadoop in a commercial manner. In 2009, the terabyte sort was achieved using 1,460 nodes in 62 seconds, and a petabyte sort was done in 16.25 hours using 3,658 nodes. As you can see, when Doug Cutting started the project around 2002-2003, they could not scale beyond 10-20 machines. Now 3,658 machines are working together in order to do a petabyte sort. And so Hadoop becomes a very popular project and lots of companies started coming in. In 2009, Doug Cutting joins Cloudera and the Hadoop market shoots up. More and more companies started using Hadoop, and here we are. Hadoop has become a major technology in big data space and is being offered in the cloud. What is Hadoop? Hadoop is an open source project for reliable, scalable, distributed computing. The official site for Hadoop is hadoop.apache.org. When you get a chance, visit the site to look at the Hadoop project and the various sub-projects. You can even download the Hadoop software from here, install it, and make it work within your machine. It works in a single machine or across distributed machines. Okay, let's look at Hadoop from a big picture perspective. What Hadoop does is it takes commodity hardware. In this case, I have 1, 2, 3, 4 racks. Each rack contains lots of servers and storage. So Hadoop takes this commodity hardware, which contains a bunch of disks and cores, which is your processing, which is your physical layer, and converts it into a logical storage called HDFS, which is really a unified distributed storage. It also uses a technology called Yarn, which provides a unified computational model. And there are many frameworks that's built on top of Yarn. So really what Hadoop software does is that you can take 100 machines, install Hadoop on it. It makes the disks across all the 100 machines into a single unified disk called the HDFS, Hadoop Distributed File System. And it takes the computational capacity of all these different machines, the cores of all these different machines, the CPUs across all these different machines, and makes it available as a single pool that you can pull out of to do your computation. And there are many frameworks that are actually built on top of Yarn. What are the key principles behind Hadoop? It breaks what is called the disk read barrier. When you have a file, it takes the file, breaks it into pieces, and stores the different pieces across different machines so that you can read all these different pieces parallelly across multiple machines and process them locally. And so rather than reading from one disk and getting stuck to the bandwidth of what you can do within that disk and the computer, you're using parallel processing technologies, parallel loading technologies across machines, across disks in order to break the disk barrier. It uses scale out rather than scale up technology. Traditionally, we scaled by getting bigger and bigger hardware, which is vertical scalability. Hadoop uses horizontal scalability. Let's add more and more machines. You bring code to data rather than data to code. One of the great things about Hadoop is that when you write a job, a MapReduce job, and when you submit the job code is actually moved to the data. What do I mean by this? Your actual code, your jar files, your Java classes are actually copied across all the machines where the data is located, and the computation is done within that machine. In other words, you move the code to where the data is rather than move the data to where the code is. It's a paradigm shift. This is one of the greatest achievements of Hadoop, which is really big data processing. That is, move the code to data rather than data to the code. It deals with failures in a nice way. When a machine crashes, not a problem at all. There may be another machine that may have a copy of this data, because whenever you put data in Hadoop, HDFS, the data is broken into pieces, kept across multiple machines, and it's also replicated. So another machine that has a copy of the data will take over the task. It abstracts complexity of distributed and concurrent applications. If you have ever built a distributed application that has to manage tasks across multiple machines, it's quite complex. You have to worry about locking. You have to worry about concurrency in your application code. You don't have to worry about any of those things when you're doing distributed processing using Hadoop, because all the work is automatically taken care of by the framework. There are two major releases of Hadoop. There's the Hadoop 1.x, which is also called Classic MapReduce, or MRV1. Many organizations used to use this. Now those organizations have started moving away into Hadoop 2. There is also Hadoop 2, which is also called Yarn, yet another resource manager. It is the new and improved version of Hadoop. And the great thing about Yarn is that it has the capability to have many different frameworks run on top of Yarn. In Hadoop 1, you can only do MapReduce, whereas in Hadoop 2, there are many different framework, many different processing technologies that have come about, like Days, like Spark. These technologies are built on top of Yarn. They can run on top of Yarn. So the idea behind Hadoop 2 is if you're going to be having 100 machines, you might as well use it for different types of processing. In this class, we're going to look at Hadoop 2 since that's the most popular one. So let's look at the Hadoop 2 technology stack. At the lowest level, you have the common libraries and utilities, which is your Hadoop Java classes. Built on top of that is the HDFS distributed storage, which is the Hadoop distributed file system. Built on top of that is the Yarn distributed processing platform. Yarn stands for Yet Another Resource Negotiator. It's a generic computational platform. Built on top of that is the MapReduce distributed processing. Built on top of that is the MapReduce distributed processing. Built on top of that is high-level query language called Hive, where you can write your queries in SQL-like syntax, which will get translated into MapReduce programs, or use a data flow language called Pig scripts, which also gets translated into MapReduce distributed processing. But then Yarn has several other frameworks like Days, Spark, and there are so many other frameworks that are coming about that can run on top of Yarn if you want to do other kinds of processing using your cluster of machines. On top of HDFS, there is also something called HBase, which is a NoSQL database that is also available for you. The point I'm trying to make is that the Hadoop 2.0 technology stack is the core Hadoop, which contains the common HDFS, Yarn, and MapReduce framework. And then built on top of that are all these different sub-projects, which is the Hive project, the Pig project, and other Yarn frameworks, and the HBase NoSQL database project, which all are part of the Hadoop ecosystem. Besides this, there are also several other ancillary projects that give you other functionalities. For example, there's Flume for bringing in data, Uzi for job control, Avro for data serialization, Ambari for console, Zookeeper for distributed transaction management. So there are several technologies that's out there. And when we talk about Hadoop, we don't really mean just the core Hadoop that I have listed here in the gray. We also mean all these other technologies that we want to use. Here's the description for the Hadoop common module. The Hadoop common module contains common utilities and libraries that support the Hadoop project, for example, configuration, the file system API, the compression of the file system, the RPC communication that's taking place across the different machines, the serialization format. All those things are part of the Hadoop common module, and all this is written in Java. And by the way, Hadoop is actually written in Java. There are all these other ecosystems that could be written in another language, but the primary core Hadoop is written in Java. HDFS is the Hadoop distributed file system, which is distributed, scalable, and portable file system. There are several client APIs available. The Hadoop distributed file system itself is written in Java. You have clearly the Java API for CRUD operations, create, read, and update and delete of files, and directories, of course. There's also a C API available, there's a command line interface available, and REST API available. The point I'm trying to make is if you have 100 machines, you install Hadoop on it, and if each machine has 1 terabyte of storage, 100 machines will have 100 terabytes of storage. Now, the HDFS file system will make it look like a single 100 terabyte storage. That's really what HDFS allows you to do. How does it work? It works because there is something called the name node, which is the brains behind the HDFS, that is the master controller, that keeps track of where all the different files are, where all the different blocks are. There are things called data nodes, which are slave daemons. By the way, name node is a daemon. Data node is a slave daemon that is actually responsible for reading and writing data to the local file system. These are different blocks that need to be written to the local file system. The clients that want to create a file, delete a file, always communicate with the name node for metadata information, and then they communicate directly to the data nodes to read and write the data blocks. Let's look at this using a picture. So in Hadoop architecture, there's a master-slave architecture. The master contains the name node daemon. The name node daemon is the brains of the distributed file system. The slave nodes run the data node daemon, which are writing data to the local file system. When the client wants to create a file, it talks to the name node. The name node says, oh, okay, if you want to create a file, well, you may want to break the file into blocks, and those blocks will be placed in these different machines. And then the clients communicate directly with the data nodes so that the blocks can be written across multiple machines. And there will be replication of these blocks so that there is duplication and redundancy. Let's look at the yarn architecture. Built on top of HDFS is yarn. Yarn stands for yet another resource negotiator. Built on top of yarn or other frameworks, it could be the MapReduce framework, it could be the Thais framework, HBase framework, Storm, Giraffe, Spark, OpenMPI, and other frameworks that allow you to do processing in different ways. For example, Storm allows you to do streaming processing. Giraffe allows you to do graph processing. MapReduce allows you to do batch processing. Thais allows you to do interactive processing. Different kind of processing technologies can be put on the Yarn platform. That's really what Yarn gives you. So what is Yarn? Yarn is a pluggable distributed computing architecture. The client programming model is that you can write MapReduce programs in Java or other languages using Hadoop streams or pipes. It also supports other distributed computing technologies. We talked about that, like Storm and Giraffe and Thais. So rather than you writing low-level MapReduce jobs, you can actually use some of these interactive or scripting languages. How it works is that in Yarn, there is something called Resource Manager, which is the master daemon, which manages the resources that are in the cluster. It's primarily managing the computing resources in the cluster. The Resource Manager assigns an application master for a job that is submitted. The application master is responsible for negotiating for containers. These containers are the various tasks that are going to run across multiple machines. Now, which machines are they supposed to run? Well, that's controlled by negotiations between the application master and then the resource manager. And then there are things called node managers. These node managers run in the slave. These node managers are the ones that are responsible for running the map and reduce tasks in the various containers across multiple machines. So let's look at the Yarn architecture, the MRv2 architecture. A client may submit a job to a resource manager, which is a master daemon, and then the resource manager will launch an application master by communicating with a node manager, which is a slave daemon, and then the app master will negotiate with the resource manager to figure out what are the different containers it needs, and so it launches all these containers, and these containers are where the different tasks are going to run. And eventually, once the task is finished, in fact, once the job is finished, because all the tasks are finished, it goes back to the client saying the work has been done. The important thing to realize is that the MapReduce architecture or the Yarn architecture is built on top of HDFS. So if you look at the architecture now, you see that in the master, there is the resource manager, which manages the work management, and the name node, which manages the data management, these are the two master daemons. And then in the slave machines, you have node manager, and then the data node, which actually launch the tasks, which are containers. That's what the node manager launches. And then the data node actually does the actual order of writing to the local disks. So the master daemons are resource manager and name node. The slave daemons are node manager and data node. There's also something called secondary name node, which is really used for backup of the name node. But as you can see, it's a master slave architecture. There'll be one master and several slaves. Now let's look at the MapReduce architecture. MapReduce is the native programming model as part of Yarn. It's the programming paradigm for distributed processing across many nodes that comes by default with Hadoop. The client programming model is when the client, which is you and me, when we want to use MapReduce, in a distributed environment, we would write or author map classes and reduce classes, which are really map tasks and reduce tasks, package it up into a job and submit the job. These programs are typically written in Java, and so you'll write a map class, you'll write a reduce class, you will also write a main class, compile them, package them into a jar file, and then you submit the job. When you submit the job is submitted to the resource manager, and the resource manager will break the job down into pieces, work with the name node and the data nodes so that the jobs can run across multiple machines. Like I said to you, there's a lot to MapReduce processing. There's an entire course devoted to it. But for now, all I want you to understand is that when you submit a job, it gets broken down into tasks that run across multiple machines, and then the job is completed and it returns back to the client. The programs can be written in other languages also, using something called streams and pipes. How does it work? Well, like I said to you, there is the resource manager and the application master, which are the brains behind the Hadoop processing, and then the node manager, which actually launches and runs the MapReduce tasks in containers. Well, let's look a little bit deeper into the MapReduce programming model. The MapReduce programming model imposes key value for its input and output. It defines the map and reduce functions. The map function takes a key in and a value in, and the map function will produce a list of key 2 and value 2. These are all types: key 1, value 1, key 2, value 2, key 3, value 3. They're all different data types. Then the output of the mapper goes into the reducer. The reducer will take a key 2, which is a different data type, and we'll get a list of values, which is a list of V2s, which will process in the reducer and will generate a list of key 3 and V3 types. Now, this may sound a little confusing to you because you haven't really done any MapReduce programming. Just bear with me right now, and I'm going to kind of show you an example, a problem example. The map function is really applied to every input key value pair. The map function generates intermediate key value pairs. The intermediate key value pairs are sorted and grouped by the key. And then the reduce function is applied to a sorted group of intermediate key value pairs. And then the reduce function emits the results. This is really the entire MapReduce processing. Now what I'm going to do is show you this programming model using an example. Here's the problem. Let's say we have a file. The file contains 3 lines: 1 fish, 2 fish, red fish, blue fish, black fish, blue fish. This is the file. It contains 3 lines. What I would like to do is I would like to take this file, process it so that I can know what the list of unique words are and how many times those words appear. Now, it so happens that this file is just 3 lines long and there's only so many unique words in it. But what if you have 10,000 files? And what if you have each file to be 2, 3, 4 gigabytes? Right? Then we need distributed processing technology. Now, the cool thing about Hadoop MapReduce is that when you write a program in Hadoop MapReduce, it doesn't matter whether you're working with one file in one machine or 10,000 files across multiple machines. The same program works. Let's see what the framework does with the input. Well, the framework reads the input source as records, and the key is really the byte offset. So the key is the byte offset within the file. See, this is line 1, which is record 1, line 2, which is record 2, line 3, which is record 3, and this is at the byte offset of 0. This is at the byte offset of 18. This is at a byte offset of 37. And so when it goes to the mapper, it's 0 and 1 fish, 2 fish as the key value pair that goes about. 18 red fish, blue fish as the key value pair that goes about. 37 and the value of black fish, blue fish goes into the mapper. So let's look at what happens in the map phase. In the map phase, each line is sent to the mapper. The mapper does the processing and then generates the output. Mapper takes the line, generates the output. The mapper takes the line and generates the output. So each record is processed by the mapper. Well, the map function output is intermediate. That's not the real output of the job, it's intermediate. And the map function has the opportunity to generate 0 records. In other words, the map function may take a record and may process no output and may generate no output. Or it can take the input and generate only one output or one key value pair as the output. Or it can take the input and generate more than one key value pair as the output. Now in this case, we are doing word count. So the algorithm here is, let's take every line and parse the line and generate the word with the number 1 associated with it as the key value. So when the first line is processed by the mapper, it is going to generate 1 as the string, as the key, with the value 1 as the value. Fish as the key and value 1 as the value. 2 as the key and value 1 as the value. Fish as the key and value 1 as the value. In the same way, it will take the second line and process it. Red as the key and value 1 as the value. Fish as the key and value 1 as the value. You get my point. So by the time the mapper processes these 3 lines, what comes out of the mapper is a list of key value pairs. 1, 1, fish 1, 2, 1. See? 1, 1, fish 1, 2, 1, fish 1. And then red 1, fish 1, blue 1, fish 1. Red 1, fish 1, blue 1, fish 1. Black 1, fish 1, blue 1, fish 1. Black 1, fish 1, blue 1, fish 1. That's what is generated. What the framework does is that it does something called shuffle and sort. The framework basically groups by key the key value output of the mapper. So it's going to do some grouping. Well, these are the keys, so it's going to group by key. Well, there's 1. 1 is right here. And then it puts a list of values. Well, there's only one value with the value 1. Then there's fish. Well, what are the different fishes that are there? Well, here's a fish, 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 here's a fish. That's 1, 2, 3, 4, 5, 6 ones. 1, 2, 3, 4, 5, 6 ones. That's right there. And then there's a 2. And there's a 1, 2s. There's a red. There's only one red. Blue. There are a couple of blues. And black. There's only one black. So as you can see, it takes the key value output of the mapper and groups them. That's what the Hadoop framework does. Not only does it group it, it also sorts it. And so this group is sorted as black 1, blue 1, 1, fish 1, 1, 1, 1, 1, 1, red 1, 2, 1. As you can see, this list is now sorted. Now, this output is what is passed to the reducer, to the reduce method. Okay, so what does the reducer do? Well, the reducer sees key and a list of values. In this case, the list of values is only 1. Here, blue, and list of values. So the reducer, which takes a key and a list of values, can do whatever it wants to do. Well, the reduce function has the opportunity to generate no records for that particular input record, generate 1 record, or generate more than 1 records as the output. In our case, the reduce function is going to generate a key value pair, and the value is going to be just a single value. So it's going to generate black 1, because there's only one of them. It simply put that 1 out here. Blue 1, 1, well, it added the 2 ones, and so it put blue and 2. Fish 1, 1, 1, 1, 1, 1, that's fish is 6. 1, 1, red 1, 2, 1. So by the time the reducer was done, you ended up getting a list of all the words in the input file with the counts associated with it. Now, the important thing to remember here is that we took a single file, we wrote a map and the reducer function, we processed it. But we all did it in a single machine, in a single process. The reality is that that's sequential processing, but there can be multiple machines that can work together. So if you have a really large file, the large file will be broken down across multiple machines, and each machine will run one or more map tasks, and each map task will process its output. So as you can see, there's a map task, a map task, a map task running on 3 different machines. This is machine 1, machine 2, and machine 3. And they generate their output, and those outputs are then sorted and shuffled and sent to the appropriate location so that the reducers that are going to be running across multiple machines, machine 1 and machine 2, can process by doing whatever it needs to do. In this particular case, it was counting and generate the output. And that's really what distributed processing is all about. Hadoop word count is a very common example of understanding Hadoop MapReduce processing. Once again, I apologize to you. There's a lot to Hadoop MapReduce processing. I wanted to give you some sense of what Hadoop MapReduce is all about, and that's why I try to give you this overview. But like I said, there's a lot to it than what I showed you over here in terms of programming. There are also a lot of Hadoop sub-projects that's out there. There's the Apache HBase project, the Storm project, the Sentry project, Thais, Scoop, Uzi, Kafka, Nox, Ambari, Cassandra, Drill, Chakwa, Giraffe, Cassandra, Mahout. There's so many projects that's out there as part of the Hadoop ecosystem. It's huge. All these projects, all these sub-projects run on top of Hadoop. Here I've actually categorized them. For example, if you want to do data integration, in other words, you want to bring in data into your Hadoop ecosystem, you can use Scoop, Flume, Chakwa, or Kafka. If you want to store data in a specific format, you can use data serialization projects like Avro and Thrift. If you want to do NoSQL processing, you can use HBase and Cassandra. If you want to do analytics, you can do Pig and Hive. If you want to do graph processing and analytics processing, other kinds of graph processing, Giraffe, Storm, Drill, Thais, Spark, all of those other technologies. If you want to do manage your Hadoop cluster, you can use Ambari. If you want to do orchestration, you can use Zookeeper for transaction management, Uzi for job management. If you want to do data intelligence, machine learning, you can use Mahout. If you want to do security on top of Hadoop, you can use Nox and Sentry. If you want Hadoop dev tools, there is something called the HTT project. So there are so many projects that's out there. When you talk about, I want to use Hadoop, you not only talk about the Hadoop core project, but also many of these projects that you want to bring in order for you to do your distributed processing or big data analytics or business intelligence. In terms of Hadoop distributions, there is of course the open source Hadoop distribution, which is found at hadoop.apache.org. But then there are other commercial distributions. Now the commercial distributions are really companies that have taken the open source distribution. They don't really charge you for the Hadoop software because it's open source software, but provide you support. So there is the Cloudera Hadoop distribution. There is the Hortonworks HDP distribution. By the way, the Cloudera distribution is called the CDH distribution. The Hortonworks distribution is called the HDP distribution. And then there's also the MapR distribution, which is the M series distribution, like M3, M5, M7, and so on and so forth. So these are other commercial distributions available in the marketplace. In summary, in terms of Hadoop history, Hadoop is based on a paper from Google on GFS and MapReduce. It is an open source project by Doug Cutting and Mike Caffarella. Although Doug Cutting is considered to be the master Hadoop architect, who is also the chair of the Apache Open Source Foundation. Hadoop versions, there are 2 major versions. There's the Hadoop 1, which is also called Hadoop MRV1, and there's Hadoop 2, which is also called MRV2 or Yarn, yet another resource negotiator. The Hadoop 2 technology stack, which is the Yarn stack, is the most popular one now in the marketplace, and that's what everybody's using. You should be using that as you move forward into Hadoop. It has the distributed storage layer, which is really the name node daemon, which is the master daemon, and the data node daemon, which is the slave daemon. There is also a secondary name node daemon, which runs in the master or in a different machine. You can almost treat it as a master daemon. It's not really a master, but it's kind of part of the master. It takes over when the name node goes down and you need to bring a second name node up. this secondary name node is used, although it doesn't instantaneously do that. Distributed computing, it uses the resource manager daemon as the master daemon for distributed processing or distributed computing. There's also the node manager daemon, which is the slave daemon. And then there's the application master for every job. There is also something called the history server, which is really keeping track of all the jobs that have been submitted. And there are these things called containers, which are really your actual tasks jobs, which are really your tasks that are running across multiple machines. In terms of programming, there is the MapReduce programming, in which you write the map function and the reduce function, you package it up, and then you submit the job. You can write these map and reduce functions in Java or in one of many other supported languages using Hadoop streaming. And there are many Hadoop subprojects, Hive and Pig for high-level analysis. There is also HBase for NoSQL database processing. And there's also Ambari and Spark, Ambari being used for management and Spark being used for real-time and other analytics processing technology. Now, that was a lot of stuff about Hadoop in a very short lecture. Like I said, there's an entire course devoted to Hadoop, but I wanted to kind of give you some idea of what Hadoop is so that you can make sense of the AWS EMR managed Hadoop service in the cloud. The one analogy I can make is, it's because you understand relational databases like Oracle and MySQL, you were able to understand the RDS service that was available as part of AWS. Only because you understood application servers like Tomcat and Apache and JBoss, you were able to understand AWS service such as Elastic Beanstalk. In the same way, only if you understand Hadoop can you really do full justice to AWS EMR, which is a managed service in the cloud by AWS. Anyway, so hopefully this gives you some idea so you can continue on with the rest of the module.